just a quick mic check, see if I'm picking up the right audio.
Hey, Ryan, I'm here now. If you could allow me to screen share. Thank you.
All right, first one will probably be a little bumpy, but we should be streaming, and we'll try and get
Okay.
it all set up.
We'll give it a minute or two for people to get in here.
Yeah, a lot of little moving parts here at the moment, trying to get used to this.
Yeah, for sure.
While we're waiting, can you answer a question real quick?
I can try.
Um, is there a trick to going from one room to another? Do you have to leave that room and then go to your list and launch this room, or can you just, or is there a different way, a different path to get there?
I believe you do have to leave.
Okay.
They said earlier though that you can watch some on YouTube while you're in a Zoom room. So you could have a YouTube in the left corner and then stay in the Zoom room for the one you really want to watch.
Yeah, I just didn't know if you click the link, if it kicked you out of the previous room and then let you join this one, or if you had to leave the previous room and then click the link.
Typically, when you click the link, it'll say leave this room and join the next one. So that's
Got it.
Right.
Thanks.
And just for the people that are entering their stuff into chat, we're not giving any prizes in the presentation here or most presentations, so no need to enter that. There will be at the closing ceremony though, so make sure you attend that at 5 o'clock tomorrow if you're interested. So I'll give it another minute or so before we get started into too much.
yeah.
I
we're a
think I
couple
can speed
minutes
mine up
over.
enough.
Okay.
And I'm the next presentation anyway.
No, that's right. So we got you covered.
Yeah.
Yeah, looks like people are still coming in.
Right. And congratulations on winning, Ryan.
Thank you. I was kind of like, I think I won something. I heard my name. Playing around with OBS, so.
Exactly.
I assume you'll let me know what it was, yeah?
Yeah, I don't remember. I remember seeing your name. That's about it.
That makes two of us, so.
Exactly.
So I guess I could start recording here too as well.
Oh, yes. Oh, should I stop my share so you can do that other slide?
You've got it up. So,
okay.
Well, except for the presenter, but just
right.
How about for this one? Let's go with what
okay.
we got at the moment.
That'll work.
Yeah, like I said, then it'll let me have time to. All right.
Yep.
So I think I actually have to go over this window and hit record. And recording to the computer, correct?
Yeah. Yes, I am.
All right. All right. I should also be recording now.
Okay.
All right. It seems like we're pretty stable for numbers for a little bit that I've seen. You want to get started?
Sure.
Okay, so we've got those. So thank you. Welcome to the 2021 Virtual Christmas Summit, brought to you by Boscoyo Studio. This presentation that you're in is sponsored by RGB Sequences, so thank you to those two folks. A reminder, during the presentation, please do not unmute or interrupt the presenter, and feel free to put any questions or discussions into chat. So you're in right now to listen to John DePlanch talk to us about megatrees and how guy wires can help you. So thank you, John.
Thank you, and welcome to everybody for this. Hope you're enjoying it so far. Great to kick this off. Sorry that things went a little long in the opening there, but we got people here, so hope you're interested. This presentation is on how guy wires help your mega trees. And I've presented on this before. I'll go into that as we're going through here. But basically, if you've seen any of my other presentations, I talk about how guy wires can help prevent the failure of your mega tree if they're properly designed and installed. They're a great way to keep things standing upright and will help you out tremendously. I am a huge proponent of using guy wires whenever you can. I have talked twice before, and Walter Monkhouse has talked on some presentations about megatrees. So I'm not going to go through everything with megatrees. What I'm going to do is, after those presentations, I will usually get a bunch of private messages with people asking me, I didn't quite understand. And usually it's about why are guy wires so useful. So that's what this is going to cover here. A little bit about me. I am a licensed professional engineer, a structural engineer, so I do know what I'm talking about when it comes to the parts and pieces and all that. I'm a bridge engineer. I make sure big trucks can drive over the bridges and they're not falling down. So designing a megatree is not all that difficult. They told us to add some stuff in here about us, but I'm not going to do too much there. They also told us to add a little tidbit here that people may not know. Well, your street light poles are actually quite heavy. They are not light poles. So yeah, you got to bear with a couple of bad puns if you're going to be in this room. I apologize in advance. So this is a basic introduction of how guy wires help. It's not a detailed design. It's not telling you how to construct it. There's a lot of simplifying assumptions I'm making in here. For example, the weight of the wires, the weight of the pole, the weight of a lot of things is not taken into account. I'm getting into some basics here, and every situation is different. There's no one size fits all thing that I can tell you for every mega tree. Everybody's located in different areas. Some have slopes, some don't. There's all sorts of things there. This is to give you some background into why the guy wires are helping, not tell you how to design an entire thing. There are, if you go to videos.xlights.org, 3 presentations I would recommend watching. If you search for them, it's the X Essentials Season 1 37. That was Walter Monkhouse. And then I did these 2 here. If you can watch that, that would be fantastic. And I would like to point out, despite the fact that we've given these presentations for the last 3 years, megatrees still fall over every year. There's a windstorm that takes out a bunch of them. No matter how much we're talking about, it seems to happen. Everybody last year, the focus seemed to be on pixel fires, and oh my God, this is a horrible, horrible problem. Well, I still see megatrees as being a really bad problem. The problem there is, the difference there is that fires can burn down your house or something like that. Where a megatree, it falls over, then you're pretty much done. That's why it doesn't get quite the attention, but I think it's still an issue. So I'm gonna ask a little question here. You don't have to respond, but I'm just kind of curious how many people have seen photos or videos of a megatree failure. Feel free to raise your hand or put it in chat if you want to. You don't have to if you don't want to. But my guess for that is people have probably more than 90% of the people in here have seen that if you've been in the hobby for any amount of time, and maybe even have had it happen to them. It's probably a smaller percentage that happened to them, but if you watch the forums, you'll see quite a bit. Next question is, how many have seen a mega tree failure that had guy wires? Next question for that, my guess, about 50%. And I'm going to say that happens quite a bit, but usually when that happens, it's because the guy wires failed or they pulled out, they weren't quite strong enough. So my last question is, how many have seen pictures with guy wires that didn't fail first and the mega tree failed? I would guess very, very few people, probably less than 5%, because generally speaking, the pole is not going to fall on its own if it's well guided down to the ground and has a stable base. There's no reason that it would fail unless you have something wrong with the pipe, something wrong with the cable holding it up if you're using the 2-stage system or something like that. But it's very, very rare that things like that will happen. So guy wires, if you just look at these percentages, again, these are my guesses, but it's based on what I've seen out there. Adding guy wires really, and if they're installed properly, will reduce your chance of something falling down. So I'm going to get into a little bit of background here, some science stuff that you probably slept through in high school or maybe college or something like that. Some of you might have been interested, but not everybody. But I'm going to talk first about capacity and demand. Capacity is how much something can hold up. Demand is how much you're asking it to hold. Pretty simple, pretty basic definitions. But we'll look at this as just a cup. A cup over here on the left-hand side, the capacity of all these cups are the same. The demand is different. As you add more water or fluid to it, it gets bigger. So I'm going to say these are all 1 cup capacity containers. The demand I've increased over here. And I'm going to talk a little bit in my presentation about either the ratio or the factor of safety. The ratio is just the demand over the capacity. Or I'm sorry, the capacity divided, or demand divided by capacity. And I think I messed that up over here. Factor of safety is when you divide the demand the other way. But basically what we're looking at, what's important here is that you want your capacity to be greater than your demand so that things are safe. When you go over here, if you're trying to put 2 cups of water into a 1 cup container, it's going to overflow. That doesn't work. As we go farther to the left, we get better. 1 on 1, it just brims the top, and then it goes down from there. Now, and I put in there that spilled. Now, where you want to fall in this range is really up to you. I'm not sure where it's going to be. What I'm going to try to show you is that we're going to try to make it closer to this end when we're doing things, but you don't have to be way down here. It's really a personal preference type thing. How much risk are you willing to take? And to just go along with the cup analogy, there's 2 different things you can look at. If you have a child that you give a cup to and they're outside and you fill it with water, you're probably not worried if they're right up to the top of the cup there and your capacity and demand are almost equal. If you give that same child the same cup full of fluid like that, but instead you give them grape juice and it's inside on your nice brand new white carpet, you don't want them anywhere near this edge of it. You want them way down here, possibly so much that there's barely anything in there. So it's all the situation. There is no one thing that covers it all where we should be. It's how much risk you're willing to take with something like that. So, and again, it's less safe as we get over here, but over here, we're less efficient. We don't want to be out there putting up these huge guy wires onto our mega trees that are doing something that's going to hold up a hurricane if we're not anywhere where we're going to get tremendous winds, but we're all going to get some winds at some point. So how do you make it more safe? Well, let's say if you got a cup that holds a cup, there's 2 things you can do. You either can put less fluid in the cup or get a bigger cup. When you do things like this with mega trees, it's a little bit strange because you can't really reduce the capacity. You can't say, well, I'm just not going to have any windy days. That is not possible. So what we're going to do is we're going to try to increase the capacity for the most part. But when you do add the guy wires to it, it actually reduces the demands as if we were going this way on the pole. And we're trying to prevent the pole from failing, not necessarily just protect the megatree as a whole. So we're spreading the load. So we're going to be doing a little bit of each of these. And that's, I just kind of wanted to cover that so you see that there's a difference of what we're doing. Sometimes we're changing one thing, sometimes we're changing the other. But in both cases, you can see here, either way we do, we've made our factor of safety better, and that's what we want to do. So do you know the capacity, the demand, or both? When you're designing a mega tree, you probably don't know either one of them if you're not an engineer, which that's fine, dandy. But we're going to try to give you some information on how you can do that. And I'm going to talk, since we're talking about guy wires are a lot like a string on a balloon. The string is going to break at some point. That's its capacity. The number of balloons that you connect to it is how much force goes through that string. The capacity is not a real force. It's just the maximum force that you can put on there. So if you have just one balloon on there, it's maybe pulling up 1 pound. If you had a bunch of balloons, it might pull up on 10 pounds. Even though the string down here at the bottom can hold 10 pounds, it's not pulling down on these until all of those are there. So capacity is a little bit strange in some respect, but again, go back to the cup. The cup has a capacity to hold a cup, even if you only put half a cup worth of fluid in there. So hopefully that makes sense. So I'm going to talk a little bit about levers here. Again, going back to some high school things that you probably learned and have forgotten about. A lever consists of several things. It's got a rigid beam so that you can move it. It's got a fulcrum where it pivots. It's got some effort force that you put on one side and output force that you put on the other side. Our megatrees are going to act a lot like this. So I'm just giving you some background here again as to why this helps and how our guy wires are going to help this. And most of you have seen something like this at a park at some point or another, I'm sure. Maybe hit it. So using our logo there, let's put 2 Bernies, 1 on each side. We got them there and they're twins. Does this move either way? No, it doesn't. Why doesn't it? Because they're both equal weights. They're both equal distance from the center. What's important when we do this, the mathematical formulas, nobody's going to have to be taking a test on this or anything, but the distance from the pivot point to where the load is applied multiplied by the weight of the load determines how it moves. If these are equal, which they are here, we'll just say he was a 100-pound Bernie 3 feet away. These forces are equal, going through the math there. That means it's in equilibrium. That means this doesn't move. It's going to stay perfectly still. If somebody like lifts up or pushes off with their feet, it moves. But if you were to just balance out there, it's not going to move whatsoever. If we have a bigger Bernie on one side and a smaller Bernie on the other side, what happens? Well, the distance stays the same, but the weight over here on this side increases. This side is now bigger than this side. I'm sure everybody knows what's going to happen then. This is a bigger thing. It's going to push down because that number is bigger than the other side, and it tips and goes down to the ground. This side over here, you'd have to add more weight to get this side to come back up. And if you have something like this, if you've ever been one of these at a park and you had a little brother or sister, or you were the little brother or sister, and you had the one that was heavier on the one side and lighter on the other side, this was never fun to play with because one was always in the air and then one was just sitting on the ground, holding them in the air so that they would scream and yell. So why does this stop? Well, it stops because it hits the ground over here, and the ground is our reaction. If we're going to megatree poles, which I'll show you later, we don't want the ground to stop our megatree from tipping. We want to stop it before it hits the ground. Hitting the ground is a bad thing. That's what we're going to consider a failure. So the ground reacts, pushes back up, and does that. But that's something we're trying to prevent. But once the ground is moving on it, this goes back into equilibrium because the ground reacts to the force that is necessary to put it back in equilibrium. The ground is never going to push up more than the load that's being applied to it. If the ground was able to do that, as you're walking down the street, you would suddenly fly into the air. The ground exerts a force, but it's a reactive force, not a pushing force. And this basically just shows, because we have 100 pounds on this side and we're reacting at the same on the over, the 200 pounds here, we just take the difference of them and we have the 100 pounds pushing back there. Again, showing a little math for those who might be interested in something like that. I realize a lot aren't, but this does kind of build to what I'm getting at later. To understand this is important. So again, the ground causing equilibrium is not a good thing for a megatree with the pole anyway. With the base, that's fine. So let's say we've got our 2 Bernies, 2 same size Bernies again. We're moving them up and we move the one in a little bit closer. What happens there is we're changing the distance. Let's say we made this distance half away from the pivot point as the other side. Still the same weight, but if we take the weight multiplied by the distance on the one side, the weight multiplied by the distance on the other side, these two are again no longer equal, so we're not in equilibrium. We've got the case where this side is bigger, same thing's going to happen, that side goes down and pushes down. Pretty basic concepts for the most part. Again, I don't want to bore you with all the details of the math. It's on the slides if you want to take a look at it later on. I'd be happy to share the slides or walk through somebody. But whenever you have a load imbalance, you get movement until it hits the ground and the ground creates equilibrium, and that's what we're trying to avoid. Now, you can play around with both of those things to make it happen. If you have a very high force on one side and a small distance on the other, multiplying these two together gives you the 300 over here. Multiplying these two together gives you the 300. If you had this properly located, it's going to stay in balance, just like the first slide that I showed where nothing moves. That's all fine and good. No problems with that whatsoever. And this is what happens with our megatree. We don't have something up at the top that's holding our wind back. We're going to play with a little bit of the locations and the weights and the forces. Again, that's equilibrium there. And we don't necessarily just have to have one load on each side of our pivot point here. We can have two loads on one side, a big load on the other, so they're not equal. They're all different distances. Who knows what's going to happen there? This is where the engineering part of it comes in, because we have multiple loads, multiple distances. As I said, I've made some assumptions in this, that this piece of pipe here, or wood here that you'd usually be sitting on, a pipe in the case of our megatree, that doesn't have any weight, or if it does have weight, that it's equally distributed and not playing into it. There's a lot of things that go into this. This is just to show you some of them. It would get more complicated with a real design, obviously. And we don't have to have everything acting on the top. You could have a force down at the bottom pulling this down. Well, what is that? That's something like a chain tying it down to the ground so it couldn't pull up any higher, which is what our guy wires are. But there's other things you could do to prevent that or get that to happen. But just know that loads don't have to be always on the top side. They could be on the bottom side. So going back to our capacity and demand talk, here you can kind of tell it's a little bit different. The capacity we're going to call over here is the left side of it, and our demand is going to be over on the right side of it. And let's just say we have a situation where somebody gave us a nice Christmas gift, but they stuck it under the one side over here, and we don't know what's in there, so we don't want to crush the box. So what we have to do is we want to make sure our capacity is going to be greater than our demand, so that this side always stays down or level, and that our demand isn't so big that it crushes the present, just as a sample here. And there's several different ways that you can keep that gift from getting crushed. What we could do is we can move or put a block underneath it, and that would allow the force that's applied over on this side to go through the block and down to the ground. That's great if you have a real situation like this with a lever. For a megatree, it's not really that practical, so you wouldn't want to do something like that necessarily. We could limit the amount of weight that we put on this side. If we keep this weight below this side, that's great, and we could guarantee that present would never get crushed. The problem is with a megatree, we're not really able to limit the load. You can't say, no, we can't have any winds more than 50 miles per hour. So again, that's not really a practical one. It is an option theoretically, but it's not a practical option. Another thing you could do is you could hook something to the sky to prevent that side from coming down, hook it to a tree nearby, a crane, a sky hook. Again, not really practical, but it is an option. So these three here, they're all things you could do, not really practical things you could do. Although this one is somewhat like a guy wire, but not quite. You could move the support. Remember I said the distance from the load to the pivot point is what is critical for some of this. So if we can move it so that this distance is greater than this distance, we get more mechanical advantage so that this load is acting more than this load. That will help us out. With a megatree, you can do that with the base and when you're positioning the guy wires. Again, I'll get into that a little bit more, but I'm just going through some options here. We add more weight to this side, then we can help guarantee that the weight will be more than it is on this side. Again, we can't control what this is going to be, but we can guess what that is going to be and put a lot of weight on that side. Or we can put a chain here down to the ground that would prevent this side from going up and tipping over. So what does this have to do with a megatree? I talked a lot of information there that probably had nothing to do with anything, but it gives you some background information. Because the same basic principles apply to a megatree. We're just looking at clockwise versus counterclockwise instead of just up and down with a pivot point. Our rigid beam, when we're talking about a megatree, is the base and the pole for that. So it's the same principle as the board that would go across for that park thing. Our fulcrum is the pivot point. If we're going to be tipping this over in the right-hand direction from our wind, that's your pivot point. A little bit different, but again, we're going to look at clockwise versus counterclockwise. So this is the point when it tips. The effort, I'm going to call the input force. That's our wind blowing up at the top of the tree. I'm going to assume nothing's blowing down here, or if it's blowing on the strings because they're connected at the top, at least some of the load's going to go to the top. And our load is pretty much the weight of the base and the weight of the pole itself. This is without guy wires, and so I'm going to walk through that first and then show you how guy wires help keep that in line. So again, as I said, the names are a little bit different than what we would be looking for, and we're looking at clockwise versus counterclockwise as opposed to just what side of a perk thing or seesaw tips either way. So if I have a mega tree here with a load on it, no wind acting on it, is it going to fall over? I think everybody can pretty much look at this and say, no, it's not going to fall over. All of my loads here are acting. If you take it based on this point here, you look at them, they're all going to try to make a counterclockwise movement. The ground here is going to react, push back up. The tree's not going to fall over. We're all fine and good. I put some loads on here, again, just for the math and for completeness so that you can take a look at it. I don't know how realistic these are. They seem relatively reasonable, but, and this is, the distances here are based on the Monkhouse portable pole. So that's why it's not quite a foot, just to make it somewhat realistic. So it's not going to fall over there. We have no demand, no wind at the top. Our capacity, taking the distance times the weight, if you do the math, it works out so that, hey, the capacity much greater than the demand because there's no demand. We're good, we're happy. But there's nothing, no wind, that's not really realistic. So let's add some wind in there. If this is a 10-foot tall mega tree and we add just 10 pounds of force up at the top, which if you have a big topper on there, or you put a big star on that, is not an excessive amount of force to be blowing at the top. It changes things quite a bit. Because this 10 feet is so large, even though this load isn't that small, we get 100 foot-pounds, and a foot-pound is just a measure of torque or desire to try to tip. It went from 0 all the way up to 100 just by a little bit of wind blowing. We're still having capacity much greater than our demand, but we got close very, very quickly with a small amount. If we go and if this moves a little bit because of the wind blowing like that, or if things are offset and this rotates and decreases this amount from that pivot point here, the base down here is still pretty much the same. But once this started to move the top over, it's moved and it's become less here, which decreases one of these numbers, which decreases what we have here. I also, on this, increased our wind load to 20. And I'm going to go back one slide here. This case here, we have more capacity than we have demand, so it's not going to tip the pole at all. It's not going to make it move over. It may bend the pole itself, but in theory, it wouldn't tip the base. Once we get it up to a 20-mile-per-hour wind, what happens is this tipping force gets greater than this, and the mega tree starts to want to tip over. The entire thing's going to start to move. Luckily, wind is not a constant type thing, and you don't get 20 pounds all at once. It usually builds up to that or comes up to that, and then it goes away. It's a very oscillating type thing. The problem with that is we don't know how long it's going to last. As soon as the wind starts blowing, it starts moving it, it starts to tip it because the tipping force is greater than the restoring force. It moves over, this gets reduced. If you remember on the previous slide, it was 184. Now that's dropping down to 144 because this load over here is getting closer to our pivot point. That's not a good thing. That's not something we want, and it's going to start to tip more. Eventually, you get to the point where it passes this pivot point when it's bending or moving like that. And now, instead of this force up here at the top and all that weight helping to keep it in line, it passed this pivot point, and it's now starting to want to turn that over more than it's helping. So you get past a certain point with your movement like that your tree is not going to come back because this load here, your load on it from the wind plus the offset here is greater than this. There's no way that this can come back. It's going to fall over at this point, and this is what we want to prevent. If you get to this point, there's nothing you can do to help yourself there. The weight at the top, pretty much once it passes that point, it goes from helping to hurting. You never want to be in that situation. There will also be a point too, where even if the wind stops, the wind was blowing in the last one. If it blows over in here, I've got it about a foot past. If you get to that point, even if the wind stops, your tipping load from here is so far out that it's pretty much identical here. But there is a point where once you go over that, the weight of the pole itself is just going to tip it over. And I think that's pretty much common sense with a lot of things is you take your pole, you push on it, you push it to a certain point, it's just going to tip over and not stand back up. You can do that even without the wind. So at this point, even when the wind stops, that fell over. So am I ever going to talk about guy wires in a presentation on guy wires? Yes. But again, keep in mind, this is an example only. Do not base the size of your guy wires off of this. I'm just using some theoretical things to try to give you some background information on that. So if we put guy wires, what do? This looks like a lot like what we had before. You could make the base wider to move this over if you're not adding guy wires. This increases this distance, makes your tree less likely to fall over. All fine and good if you want to do that. You could add more weight to the base. Making it bigger usually adds weight, or if you're not doing a portable hole, you can put it into the ground and that will help, or make it really, really large. That'll help. You could tie your base to the ground, which is what the ASAP pole does. It's got all those little holes on it, so you can do that. Or you can add guy wires. All four of those will help to keep your tree from tipping over. I prefer the last one, which is the guy wires, but all of these are valid. And actually, if you use all of them, you'll be even safer. So it can't hurt to do that. Again, we're getting into a little bit of the math here. This was all the same as we saw before, just with the 20-mile-per-hour wind. But now when we add guy wires, instead of having all of this force try to come down here, we get another bonus of a force here that's at a fairly tall height. And what happens is that adds a lot more capacity to us because we have some force here. We don't know what that force is. That force is a reaction, but it helps us quite a bit. So what happens is our capacity up here was 184. Our tipping was 200. This is bigger than this, so it wants to tip over. Adding these guy wires, we add in this extra force here from even with just 2 pounds going through our guy wires, it makes it so that this force here is the same as this force here. Again, it's a reaction, so it's going to want to go to equilibrium. But instead of trying to tip over, just taking 2 pounds of force through these guy wires, or at least in this direction, helps us out. That's not much force at all when you're thinking about a 20-mile-per-hour wind coming down here to this. It just spreads out things when you account for this. What I like to do is I like to ignore all of this weight here and just count on my guy wires to support it if I were going to be designing one. And that's what I'm doing here. If we add in the capacity of this, it increases it even farther. At 20 pounds, so the guy wires could take the full force. Actually, this still accounts for the weight of that, but it gets you tremendously higher than what that is there. And if your guy wires can hold even more load than you're expecting here, you're going to be even better. And this is where I was talking about a 25-pound guy wire at this location. You don't even need to account for the weight of your base, the width of your base, anything like this. This is going to stand just based on the guy wires being able to take slightly more load than the wind at the top because I'm putting them up at the top of that. One thing to consider, though, is when I was talking about those loads are the horizontal force. Depending on the angle that your guy wire makes to the ground, it can go up considerably for the actual force that's going through the wire. If you're purely horizontal going in this direction, they would be identical. But as you go more and more vertical, this starts to skyrocket. Oops. And if you were to be perfectly straight up and down, it doesn't help you at all because it theoretically goes to infinity. Where you want to stay is usually somewhere, this angle here, 60 degrees or less, so that you're only doubling the load. Once you get over that, it's really not helping you too much. So try to keep your guy wire anchors as far away from the base as you can. Realistically, it's not possible to go way out to like 15 degrees or something so that you're way out here. You're going to be close, but try to keep it under 60 degrees so that basically you've got twice the height to the distance away. So we're going back to this and this tipping. How do guy wires help this? Well, guy wires first don't allow this movement to happen. In addition to taking the load, they don't allow this movement. If the top can't get off of that pivot point, it just helps you there because we're keeping it way over here. You can't get over there. You can't get into that situation where things are going to fall over. I did see a comment in chat how you calculate the potential wind force of a particular wind speed. I would recommend watching Walter Monkhouse's presentation from a couple of years ago. He goes through some formulas and some simple things there. I don't want to redo what he talked about in there. He covered that very well. So that will help you out there, because it's based on how much area you have as well, and wind speed for the force. So there's more to why guy wires help here that I'm going to go into. Tipping is one big thing, but let's say you have a nice fixed base, nice wide base, you tie it to the ground, perfectly done ASAP pole. You still have a pole that's going to be sticking up here if it did not have guy wires, that when the wind blows, it tries to tip it over and it bends. That's what happens when your pole is relatively flexible. And you can see this here. This is from the build for the ASAP pole. I drew a yellow line in here to show pretty much what vertical would be. Walter has this, his ASAP pole nicely staked down to the ground. He pulls on it with quite a bit of force, doesn't tip over because he has the base properly done. I think he's pulling with like 70 pounds of force, but you can see how much this pole is tipping. As I said, when your tip of your pole here gets out of past your pivot point here, it's going to want to start to tip over on its own for the whole thing. He's got the base to prevent that, but look at how much bending is in there. That bending is not good for the pole. That's not always a good thing that you want to do. And that's why guy wires help that, because it doesn't allow the pole to move over like that, and then gets rid of the stresses in the pole, and your pole is what's really going to fail there. So the amount that the pole bends depends on the stiffness of the pole. And I want to point out that stiffness does not equal strength. It can if it's the same material. So if you have a steel pole, for example, and you get a bigger diameter pole, then yes, you're going to have it stiffer and it's going to be stronger. But when you start looking at different poles, if you were to use PVC, or if you were to use some type of composite material, some of those things are actually more flexible, and stronger, but more flexible, like I said. So they can take a lot more force, but they're going to be moving all over the place, and that's not necessarily a good thing. So remember, stiffness does not always equal strength. Some people will look at it and say, well, the top of my pole isn't moving at all, I'm good to go. Well, only if you have enough strength in what's standing up there. So keep that in mind. They're not always the same. So over here, let's say I have this very nice fixed base at the bottom and a wind load comes on it. This is more or less what the pole is going to look like if we put a lot of force on it. Look kind of similar to what Walter did in the previous slide. If you have guy wires that you install 8 feet up on a 10-foot pole, instead of bending way out like this, I did this to a slightly different scale, but what's going to happen is the top still goes over this direction, but there's no movement allowed where you connect the guy wires to. So it goes into this weird bending situation where it goes up and around like this. It looks kind of goofy, but this is actually better for you because it's keeping these things from bending out too far. And this may be a few inches over here that it's deflecting. This is going to be less than an inch very easily because it just can't move in this 2-foot length that much distance. Most of what anybody's going to be using for a mega tree, if you have 2 feet, even with a huge load on it, is not going to be able to move an inch, probably even sub half inch. If you had a pin base where this could rotate pretty much freely and it wasn't locked down there, it still looks very similar. It's a little different in that this will just kind of form one big U shape, where this one kind of bends, comes back into here. But on both of them, guy wires are helping you because it's not allowing the top to move that much, even if it's a couple of feet below. You do want to keep it close to the top because the closer it is to the top, the bigger that distance is, the more it helps you, but you don't have to do it 100% to the top. That's just not practical. So what these slides I'm going to show here is they're talking about the amount of bending that is going to be in the pole of your mega tree. And what I'm going to show here is I'm going to show a couple of different situations for different heights. This is not the guy wires on the tree. This is a measurement of how much bending that we have in the pole of the tree. So it's measured in foot-pounds. That's just what we use because it's bending, and that's what it's counted off as. But if I have a 5-foot tree, what's going to be happening is it's coming at the top. There's not much bending. As you go down a little bit more and more, it's that same thing. It's the amount of force that we talked about previously times the distance up to it. So if we have 100 pounds acting at the top, as you go down a foot, you'd be at 100. 2 feet, you'd be at 200. All the way down to the bottom where you have 500 foot-pounds of force in that tree. If you double the size of that tree, like I said, there's the pole height, the bending, and we're starting off with 5 foot tall, 100-pound, no guy wires installed on this. This is a measurement of where that would be. If we double that to 10 feet tall, pretty much doubles everything. You're starting at 10 feet, still starts at 0, follows the same kind of direction here. When we get down to the bottom, we got 1,000 pounds of foot-pounds of force in there. As you double again up to 20 feet, it just doubles. It keeps going, gets bigger and bigger. If we were to double the load on the top so that instead of 100 pounds, we have 200 pounds, this skyrockets to 4,000. These numbers may not mean much to you, but what I'm trying to show here is every time you increase the height or increase the load, there's a proportional response at the bottom of your pole that you're getting more and more demand on that, and you're not increasing the capacity of your pole when you do that. So you're getting more and more likely to fail every time you do that. And a lot of these ones that have the threads at the bottom, that's a weak point. That's where it's going to rust. That's where you've taken away material. That's not where you want your highest load to be. So this gets very bad very quickly when you do things like that. And this line here, I'm going to just say, let's say I picked a pole that had a capacity of 800 foot-pounds in here. 800 foot-pounds, I can do a 5-foot pole. When I get up to a 10-foot pole and I cross this line, anytime one of these lines crosses this line here, this means that I have less capacity than I have demand, and the pole is going to fall over. So if I had something that only has 800 pounds, I can't do a 10 or a 20-foot pole, or if I increase this load up at the top, it's going to fail. And here's kind of an example of showing where things are going to fail. If this pole here, and I don't know how tall this is, I'm just using this for a demonstration purpose, they had guy wires down here at the bottom, but nothing up above that. So what happens is when this load here crosses that line, it would pretty much be acting like it was at this point. It forces it to bend, it forces it to want to fall over. Another example here, this one was before it was set up, it was during assembly process. The capacity here meets the demand line, that's where you get your kink, that's where the fail happens. It doesn't happen below this point because this is the weakest point and that's the weak link in the chain, and it fails before it can get down to the bottom. So this is something you want to avoid. You never want to be crossing this line. Now, nobody here, not many of you are probably in here because you're engineers and know how to do this. So I don't expect you to actually know where this would take place. What I want to show you is what happens when you add guy wires to this. So I'm going with a 20-foot pole here as an example, 800 capacity. It looks like it would fail about 12 feet here. You're going to have a problem with this if you designed it this way. If you were to take guy wires and put them halfway up the pole at 10 feet, what happens is this line that is a measurement of how much bending is going through the pole, when it gets to the guy wire, it turns and it comes back. We're actually putting less bending into the pole when that happens. It starts bending the pole in the opposite direction once it hits the guy wires there, or not bending, it starts the force going in the different direction, and then the bending starts to decrease there and starts to turn into the opposite direction. So what happens is at the location that you put your guy wire, it stops this and turns it into the other direction. And if you have a fixed base, yes, you do get something down here, but we're stopping this at 1,000 pounds. It's coming to 500 pounds down here. Either one of those are well below the 2,000 pounds. The problem is it's still above our 800 capacity. So we still have a problem here. But if we move our guy wire up, I'll go back a step. This is if we had a pin base. This really isn't important. Theoretically, we don't know which point we're going to hit here down at the base. We're going to be somewhere between a 500 and 0. Because both of these are less than what this is in not accounting for positive and negative, that's what we care about. If we move our guy wires up to 12 feet, right where that point was that we were going to fail, you can see we're right on that line. We have our factor of safety right at 1. This pole theoretically would stand if we had guy wires there coming down, because no longer are we trying to get to 2,000, we're trying to get down into the 1,200. If we keep going up, the higher we put our guy wires, the sooner off we're changing this line. It's coming down and then it's coming down here. Again, this is not your guy wire. This is a measurement of how much force is going through there. Down here, when we had no guy wires, we were getting 2,000 foot-pounds of force going through it. If we put a guy wire here at 18 feet tall with that same force, we're only getting 200 pounds going through that. We've reduced that to 1/10 of what it used to be simply by adding guy wires. We're getting much more capacity, or we're not changing the capacity of the pole, but we're reducing the demand on the pole significantly. So we're going down to something that looks like this instead of something that was coming way out there. So the guy wires don't allow you to come all the way this way with your force. You're never getting to this line. You're not even close to this line. Before we were failing, now we're well under this line and we got plenty of room of factor of safety to go in there. And higher factor of safety is always better. It keeps us more safe all the time when you do that. So the more important part of this, though, is that the guy wires need to hold. You need to make sure that they are installed properly, that they're not going to snap, that they're not going to let go, that the anchorage of them into the ground is not going to pull out with any force that goes on them. Because if we're counting on those guy wires to pull this down, because we know we only have this much capacity, and without the guy wires, we're going to need this much capacity. If the guy wires fail and it comes down and hits here, the whole tree has failed or it has tipped over. If you're counting on it to come down like this, then you need to make sure that those guy wires are going to hold. If the guy wires fail, you reduce the capacity, you increase the demand, and you're more likely to fail. Now, keep in mind, it's not a guarantee that you're going to fail if you don't have the guy wires. Everything I went through here is basically to show that guy wires are helping you. It's not to say you absolutely 100% need them on everything, but they're relatively cheap insurance that you can add to make sure that you don't get into a situation where it is going to tip over. If you want to make a bigger base and use like a 6-inch diameter pole for the center of yours, you probably don't need guy wires. The problem is most people aren't doing that. We're using relatively light bases. We're using poles that you can pick up at a big box store that are like 1.5 inches diameter or something along those lines. They're really not designed to be taking that much bending force. They're designed for other applications. We're just using them there. So I always recommend to people, use the guy wires. They don't cost that much to do. They're not that complicated to do. And they can save you so many headaches, both from your entire pole pick falling over and your center pole from bending, that there's no good reason not to use them. So I realize I kind of went through that fairly quick and there was a lot in there that could be done with it. But I appreciate everybody coming to this. If you have any questions, I would be happy to answer them. I don't know if Ryan needs to change permissions to allow you to do that, but feel free to ask questions if you have them. If not, I'll take a look at the chat and see if there was anything in there.
Everybody should be able to unmute now. I saw a couple questions in there, but if somebody...
Yeah.
Todd Moon had a question, I think just a general, any comments on the number of wires to use in general? What would you recommend?
I always use a minimum of 3. Try to keep them equally spaced in terms of angle, but a minimum of 3, practically speaking. 3, 4, or 5 are good numbers. 3 and 4 are probably the most common, but no less than 3. That way you can accommodate it any direction coming across from there. And I did see a question in there about a simulation software. If you look up online beam bending, you can do that, but it's assuming that things are laying flat as opposed to standing up. Usually when you get into columns, they're looking at loads on the columns and it's not quite the same. And I did see a question there about the capacity of the poles. I don't like to get into the capacity, like how much it actually is for things, because there's so many variations of the different types of poles that people use with the different diameters. And some people are not using the same type of materials for them. Some are using rigid steel, some are using, I don't want to say wrought iron, but iron poles, some are using aluminum. There's so many different things that you can use. It's tough to figure out what that is.
Looks like there's a question about anchoring, stakes. How would you recommend to anchor the guy wires?
Yeah, I recommend using stakes that are as deep as you can afford to get them. If you can add additional weight to that, I would recommend that so that they don't pull out. A lot of that was covered in previous presentations that both I and Walter did. But the biggest problem that people always have is the stakes do seem to pull out. American Earth Anchor makes a great long anchor that can go into the ground, but it disturbs the ground. If you can keep something there, it's better. And if you have a situation where you can actually drop some concrete into the ground and leave it there permanently, that would be the best thing. But it's very tough to be able to do that realistically.
All right. Anybody else have any other questions, or we'll wrap it up? All right. Well, thank you, John D. And
Sure.
again, thank you to our sponsors, Boscoyo Studios and RGB Sequences. I hope everybody has a great VCS.
I've got a question if there's still time.
Oh, I think we do have a little bit of time, yeah.
Okay. You had mentioned about the coupling where people will screw the pole into the base and that is a weak point.
Correct.
If you had the option of having the coupling, having the pole at a coupling screwed into the base, or having the pole slide into a sleeve that's buried into the ground, which would you prefer? And note that the pole sliding into the sleeve wouldn't be, there's no resistance there, it just slides into it. And,
Right.
and guy wires are still used.
Yeah. If you're using guy wires, either one is going to be about equal. When you're sliding it into a sleeve, what happens is you're essentially have the bottom able to rotate a little bit. So you're kind of taking off the amount that you would be able to, the amount of force that's going to go into the bottom of it, because it's going to try to rotate. Where when you have it screwed in there, it is going to try to rotate and it may break there. But if you're having guy wires, that's reducing the amount that's going to happen. So either would be okay. It's just a matter of use the guy wires in that so you're not putting the force on the bottom there.
Got it. Thank you.
Sure. I see Bob Cox has his hands up.
Yep. I did catch earlier in your presentation that, ideally, as far as load is concerned, that guy wires at roughly 60 degrees is probably close to the ideal. What I didn't catch is the height on the pole of where you should fix your guy wires, whether that's 60%, 80% up, 90% up. Is there a recommended ideal location on any given length pole?
When you're doing the pole, if you remember back when I was going through everything, the distance times the load is the biggest thing with everything. So the closer that you can get the guy wire to where the load is going to be applied, which is generally speaking your topper, the better off you're going to be. Now, I realize that you can't really connect it to your topper or right to that, but I would get it within a couple of feet of that, and that's going to be your best bet.
Okay.
So I don't like saying like a certain percentage of the height of your pole, because I don't want to say if you have a 20-foot pole, put it at 16 feet. I'd rather see it at 18 feet. But if you can do a 10-foot pole and get it at 9 or 8 feet, then you're still going to be fine.
Okay.
So
ideally, the higher up it is, the better it is. So if you can get it to the topper, then that's the best.
Yes.
Okay, perfect. Thanks.
And basically what happens is the guy wires don't do anything above where they're anchored to. They don't help you out at all. So you're getting your protection from the guy wire connection point below is what it's helping you. So the higher up you are, the better off you are for the entire pole.
Okay. Thank you. That was a great presentation.
Thank you.
Any other questions? We still have a couple of minutes before we need to. Well, I would think that after all this great information, we should see no more pictures of failed megatrees.
That would be nice.
All right, so I don't hear anybody else. So again, thank you, John D, and thanks to our sponsors, Boscoyo Studio and RGB Sequences. And again,